Alright, time for another draftphysics.com. Debatephysics.com also, but no discussion and debate is possible, apparently. You know, just can't be done. Can't find people capable of taking the arguments I make and composing reasonable, coherent responses to them. So we're just stuck. I guess I should point out this shirt doesn't mean anything. 90% of my clothes is secondhand clothes. I'm not a sports. Who cares? Absolute nonsense. Waste of human energy. Anyway, so we're arguing between an old theory. Okay, came up when Newton was alive. And the proposal, the conflict is between a notion that all you need to know about something in the universe is its mass and its velocity, and that essentially composes its capacity to interfere with other things. It can only this times this will tell you how much quantity of this stuff we call energy there is, and it'll tell you how many bowling pins it'll knock over, how many much, whatever. And it was proposed that no, the thing that matters is this mv squared. And later they put a half in front of it. Okay. All right. And so that's what the discussion is about. All right. Is the conflict between these two things, because they're very different answers. So it all works out okay. All right. If you have something that has the same mass, so the same mass going in, same mass going out, everything's fine. But if you convert, the momentum from a heavy thing to light things, you'll lose all of this kinetic energy, half of it. And if you do the opposite, go from a heavy thing to light things, you will create free momentum. Right? Yeah. All right, so the arguments, so there's a bunch of these little experiments where they take the one mass, and we can combine it with another one mass, okay, that is inelastic, allow them to hit each other and stay stuck to each other, become a two mass, okay, and it will end up having, this will end up having two velocity going in, this is 0, and this will end up having one velocity coming out, and the momentum be conserved, but will lose half the kinetic energy disappears. And the argument they make is that somehow there was sparks or something, but obviously you could just argue that if there's going to be any noise or any vibrations or any disturbances or any heat, that you'd have to use the momentum. You couldn't keep the momentum and send it off in some other place. You can't do both things. So that doesn't make much sense. So it's really the destruction of the kinetic energy. So that doesn't really fit. Now the momentum works out fine. But we just make a subtle change, and then we just have the one mass elastically hit a two mass. All right, and then we create this weird scenario where I'm going to end up with, I start with 100 momentum, MV, and I'm going to end up with 133 MV going this way. Okay, and I'll end up with a little bonus of 33 going this way. So I'll have a total of 166. Pretty substantial increase in the momentum. So I'm making free momentum. Now, kinetic energy is conserved in this case because, they say momentum is conserved in this bizarre way where they say that this extra 33 cancels with this 33 this way, and somehow that's not real motion in the universe, and so that doesn't really knock things over, so that doesn't matter. So they're back to still having 100. I say can't be. All right, so we're really just talking about these kind of scenarios. Now, they won't show us the thing that would really just decide the issue, which is their contention that it takes 25 times the fuel, okay, to go 5 times as fast. So if I want a motor to go 5 times faster, I have to put in 25 times the wattage. So if it's going 10 revolutions, to go 50 revolutions, I have to put in 25 times as much watts as I did for the 10. I have to increase it by 25 times to get it to go 50 revolutions. Now, there's no evidence of that, so we don't have that experiment. That would be sort of the clincher. And we don't have any of these done from space. So all that stuff in the space shuttle where they could just do these simple experiments now, they don't really help us out by doing any of them. So we're stuck with these different kinds of air track versus carts. So what I've observed about the carts is that actually, you know, they do this thing, okay? So let's just use this 3 mass, because that ends up being even more interesting, because then you create 150, okay, going this way, and you create 50 going this way, okay, huge increase, and you have exactly the same velocities. So for the 3 mass ends up going the same velocity that this ends up going, leaving. So that's sort of an interesting feature. You know, and then you end up with 200 here. So you double your momentum, total motion after the collision. Because that one brings up the point that if I reverse this now, and I have the 150 crash into the 50, I'm only going to get 100 out. And that doesn't seem possible, that I could have a car crash between something with 150 momentum and something with a 50 momentum, and only 100 comes out of the crash. That doesn't seem possible. So if we could bounce these cars, you know, off walls and have them come back again and hit each other, that would be the theory, that I can push a car at 150 momentum and have another car with 50 momentum and have them hit each other, and one of the cars will come off with just 100. Doesn't seem very probable. So anyway, what I did observe is, you know, these little cars they use have a lot of wheels. You know, they call them low friction, but when you watch them, gee, they run out of energy awful fast. You know, some don't, you know, they hit and it just moves and then it goes a foot and stops. You know, it doesn't seem all that low friction. And they have a lot of wheels, and little steel wheels on a metal track. That's not exactly the definition of low friction. That's sort of a high friction, you know, high contact, very good contact. That's, you know, trains, metal on metal, is pretty good. You know, it being able to create torque. So the interesting thing, okay, so I got this drawing sort of backwards. Don't know if it really matters. Well, the two cars are the same. The interesting thing is, it says, even though this one has the extra weight, okay, it has extra 2 mass on it. If you thought about it in terms of the angular momentum, that is the momentum caught up in the wheel spinning, okay, so that's momentum you don't see, okay, because it's circular, so you don't see that momentum. So when something's moving this way and it's got wheels, the wheels mean that's a little bit extra. That's like a battery that's holding more momentum. So whatever the weight of the wheels is spinning, you have to consider that's extra, that you're not seeing. Now, that would be conserved in the sense that this wheel spinning and this wheel spinning, same difference. But the interesting fact is that when they leave, the heavy cart going the same velocity, let's just say 1 velocity, and this is going 1 velocity in the opposite direction. So when they leave the collision, the interesting fact is that the angular momentum, that is the momentum of the wheels turning, is the same. So that is conserved. So the wheels momentum, the portion of the momentum caught up in the wheels, is actually conserved. Where, you know, the linear momentum, the momentum in a direction, is not conserved. So I thought that was rather interesting when I thought about it. So on air tracks, there's no wheels, so we don't have that problem, but we also have a bunch of, you know, variation in the experiments in terms of the outcome of the experiment, so can't be too sure about that either. All right, so the simplest argument I can make is this argument of reversing it. So physicist Michael is supposed to be doing the pendulum experiment, which should be relatively decisive if it's done well. I mean, it's not as good as showing the 25 times the fuel to go 5 times as fast, but it would be pretty good. So the idea is that you have a 1 mass and you have a 3 mass. And you're going to have a nice elastic collision in a Newton's cradle. And the expectation is that I'm going to drop this one with a velocity. And so we'll just say, for the sake of argument, okay, that this one's going to end up with 4/3 of the velocity. Well, how to put it? Well, anyway, so it's got 100 momentum. So it's the same argument. It's going to have 100 momentum coming in, an MV that equals 100. And what you're going to end up with is this one leaving with an MV that equals 150. And you're going to have this one go back with a reflection of 50. And now those two things, because it is a Newton's cradle, they're pendulums, okay, you're going to get the energy back in the sense that they're going to go up into gravity and gain a falling distance, and that falling distance will allow them to regain their velocity and come back here with the same velocity. So this experiment does duplicate the fact that you're going to have 150 coming in and you're going to have 50 coming in, all right, in the small object, and then you're going to end up with just, okay, this one's going to go dead, nothing, 0 velocity, and this one will leave with the 100 momentum. So you went from having 200 momentum in, total momentum of the car crash, and only one car is going to leave with only 100, half the momentum. So you're going to destroy half the momentum. So we have the exact inverse of the 1 mass plus 1 mass equals 2. So it's just like the kinetic energy experiment. In a sense, you're going to lose 1/2 the kinetic energy in this experiment, and you're going to lose 1/2 the momentum in this experiment. And I would sort of argue that the conservation law has to exist here somewhere, and you can't make this free energy, because if you could, we would. And the fact is we can't, so we don't. And so there's something happening in these experiments, some subtle facts, okay, that are fooling people and creating this confusion. But again, the real story is this idea that it takes twice the force to create 1 velocity, you know, and 4 times the force to create 2 velocity in an object. Now, it's not what Newton said, okay, so it's not Newtonian mechanics, it's Leibnizian mechanics, and they don't call it that for some reason. They don't want to give credit to the person who invented it, and instead they want to blame somebody who was opposed to it. So even though Newton was directly opposed to it and didn't believe it, they keep calling it Newtonian mechanics when it's not Newton at all. It's not Newton's second law. Newton's second law is 1 unit of force creates 1 unit of velocity, and 2 units of force creates 2 units of velocity, and 3 units of force creates 3 units of velocity. So Newton didn't believe that 4 pounds dropped 1 foot was the same as 1 pound dropped 4 feet. Newton did not believe that. Okay, and obviously I don't believe it either. This definitely has this going 1 velocity and this going 2 velocity. This cannot possibly, this is twice the impact force that this is. This is twice the impact. Twice the force will hit the ground. They are not the same thing. Alright, so that's the summary, I guess. So the obligation is the people who are going to say, oh, how crazy can you be? How silly of you not to believe what we believe. You know, they sort of just have to explain, say, confirm that, yes, they understand that if I did have a car crash where I had a total of 200 momentum going in, let's say 200,000, I can make it so only 100,000 momentum comes out. So 200 goes into the little smashing point, and only 100 pops out. That's what they believe. in an elastic collision. That is, no fenders are bent. But even if we added up the fenders being bent. So that's the other contradiction here. So as I pointed out in another video, you do have two experiments that just don't, and the difference is whether it's elastic or inelastic. This idea of whether it reflects or it doesn't. And so you have the example of the ballistic pendulum with the bullet. So you have this bullet that has this high kinetic energy, and it goes into the ballistic pendulum, and you lose 99% of the KE. All right. And you conserve the momentum. 99% of the momentum is so you're minus 99. Yeah, I should draw it in big red letters, right? You're minus 99% of the kinetic energy, and you've conserved 99% of the momentum. So the MV is 99% conserved, and the KE is 99% destroyed, disappears. And that's a small thing hitting a big thing. When small things hit big things, you're supposed to gain momentum, not just conserve the momentum. And so the argument is if I can make the bullet bounce off, that is, if I can make a spring capable of absorbing the bullet and then shooting the bullet back, then I can double my momentum. So if I can get the bullet to bounce off, I can double my momentum in the pendulum and still have the bullet flying, which is, also, now we're talking about 300, starting with 100 and ending up with 300 total. So that's what they think is possible, that you can have a circumstance where you just put 100 in, okay, and you can get 300 out. That is, you can put 100 going this way, and you can get 200 to go this way, and you can get 100 to still go back this way. You can throw a rubber ball at a brick wall, and you just put twice the force into the wall, and you're getting the balls bouncing back with the force that you threw in. So you're quadrupling the energy, total energy in the universe. So in a sense, that would be like, it violates the internal, like say if you're alone in space, you can't move by just moving your arms. You can't just throw your hand over there and move your whole body. You have to actually let something fly off of you, okay? So you can't do anything internally, like punch your own fist, right? I mean, I could hit my own hand, and there. And, if this hand was heavier than this hand, 3 times heavier, I'm supposed to be able to create more momentum in that direction than I started with in this direction. But then they're going to argue that it took me 3 times twice as much force to move my hand in the first place. So, but we don't have any of those experiments, So anyway, so the argument is they claim I should be convinced, okay, without the 25 times the fuel or 36 times the fuel to go 6 times as fast, or 48 or 56, or you can just keep making the numbers more and more gigantic. 100 times the fuel to go 10 times as fast. 100 times the fuel to go 10 times as fast. That's what they believe is true. That if you want to go 100 miles an hour, you'll use 100 times more gasoline than you'll use going 10 miles an hour. 100 times. Not 10 times. 100 times. So, yeah, without that piece of evidence, the rest of this stuff looks like, yeah, it's interesting. Wow. But there's probably an explanation. Yeah. You can't destroy energy. And one of these things is a right answer and one of them is wrong. Newton, Galileo, and Descartes believed in MV, quantity of motion. Leibniz believed in this 1/2 mv squared. Now, Leibniz didn't convince anybody in his lifetime, and it wasn't until both Newton and Leibniz were dead that this argument was resurrected, and they did some silly clay experiments, and everybody fell for it then, for some reason. But whatever. That's the real history. That's the real circumstance. And again, people don't want to discuss it. They just want to ridicule people for not accepting their story.